predicate defined on an anomaly attributes that we just saw in the previous slide, and examples of conditions are listed below. So they are just simple predicates. And then we say that the conditions is a conjunction of these predicates. So if all of them are satisfied, then you can take an initial action based on whatever is specified by the user. Now this is the typical event condition action kind of a policy paradigm. We go a little bit further and say, because we want to give a high level language to the user to specify these policies. So we say, okay, if the initial action is, let's say, privilege suspension, then you can, in the policy itself, specify what is the confirmation action that needs to be taken, and again, what is the alternate action to be taken in case the confirmation action fails. So let's look at an example of a particular policy. Let's say a policy says that re-authenticate unprivileged users, so non-DB owner kind of users, who make a connection from inside the organization internal network with a second password for write anomalies to tables in the DBO schema. Now this is after some anomaly has been detected by the detection engine. So in terms of the policy language, how this policy can be expressed is like this. If role is not equal to DBA, that gives you unprivileged users. You have the source IP in some particular range which represents the internal network of the organization. An object type is table, and okay, the syntax of the attributes is a little bit different, but I hope you get the meaning here. And objects in this particular schema, and the SQL command, because we are looking at write anomalies, so we say insert update delete. Then the initial action is to suspend the privilege, and confirmation action is re-authentication with a second password, and the alternate action is otherwise to disconnect the user. Okay, so I hope this is up till this point it's all clear to you. So we implemented this system in PostgreSQL open source database. So we designed a schema for storing these policies. So table structure so we store the policies in a database, in database tables, and we then have a policy selection algorithm for once you have the anomaly assessment in terms of the attributes, how you're going to select this policy from the policy tables. So I'm not going to go into the details of the implementation here for policy storage. And so one particular anomaly assessment can match multiple policies. So in that case, which policy are you going to select, and which response action are you going to execute? So it's a hard problem, but we kind of do some cheating here, and we say, okay, you can specify. You give options to the user. You want to choose the most severe policy, where the policy severity is actually dependent upon the severity of the response action, where you saw that you can have aggressive actions and conservative actions, and in between fine-grained actions. So that guides the severity of that policy. Or you can have a least severe policy. So ultimately you choose just one policy, and then you choose the response action to execute. And then we implemented the notion of privileged states inside PostgreSQL. Just to give you a little bit of flavor on that, PostgreSQL maintains privileges. So it's got, at the max it can have 16 privileges. So it can fit all privileges in a 32-bit integer, and it maintains that as an ACL item for each database object, where the first 16-bit specify the privilege bits, and the rest of them are the ground options. So a particular bit, so every privilege, like select privilege, has got a particular bit mask, and the same position in the ground option bit specify that particular privilege is grantable or not. So very nice, but of course this is only possible if you have just 16 privileges. So you can pack everything in a 32-bit integer. So we just extend that we use the same data structure for privileged states, and we specify, okay, you have another data structure called ACL state item, where if a particular bit at let's say bit number 1, which is equivalent to the bit mask of select privilege, so it's tainted, and similarly for the suspended bit. And you attach again this to the database objects in the data in the database. So now I'm going to go over some of the experimental results. The objective of the experimental evaluation that we performed was to evaluate the efficiency of the policy storage mechanism, which I did not explain, and the policy selection procedure, policy selection algorithm, which again I did not present. But I think the couple of slides will just give you, okay, what was the setup? So implementation is PostgreSQL 8.3. We generated policies randomly. You select attributes and you randomly assign values to attributes, and that's how generate synthetic data. And the policy selection code was in the PL procedural language of PostgreSQL, which is PL/PGSQL. So we didn't write it in C, which would have been much faster. Anyway, just to see how it looks like. So the first experiment gives you a graph of how the policy selection time, or what the policy selection time is as the number of policies increase, which is kind of unrealistic to think that you will have 1,000 policies in the database. But this gives you an idea that the policy selection time remains constant, and that is very good in terms of the scalability of the system. So you keep adding policies to your mechanism, the selection time is going to remain constant. And it's 20 milliseconds, around 20 milliseconds in this case, but it can be brought down lower if you write your code in C instead of PL/PGSQL. And then, but as number of policies, the second graph is between number of matching policies and the policy selection time. So as the number of matching policies increase, you have a linear increase in the policy selection time, which is, I think, is also reasonable when we talk about the scalability of a system. Okay, so lots of future work in this direction. So the policy storage scheme that I did not describe, we need to, right now we can only support equality and non-equality predicates. For supporting wider range of predicates, we need to come up with a better scheme. And as I said, you can develop a formal access control model based on the notion of privileges, which is again a work in progress right now. I guess that's all I have to say.
Questions? Do you have an idea of what kind of overhead this adds to the database management system? Just accessing data, which should go, if that's in, what do you imagine an order is on top of that?
Well, that's what the policy selection algorithm experiment. So you see, could be at least 20 milliseconds if you just look at this experiment.
But relative to just a simple access.
That's a very difficult question to answer. It's going to depend upon the system under consideration. So I need to run some actual benchmark simulations to see how, in terms of, like you're asking, percentage wise, how much is going to increase, affect the performance of the system. But I don't have precise number for you. Yeah.
What would you consider an acceptable kind of threshold or an acceptable amount of overhead?
That should actually depend upon the system under consideration, but let's say for a normal database, less than 5% should be good. But yeah.
Let's say in case of SQL injection, the query that's actually going to be formed, it may not be like harmful sometimes. It just manipulates the query to be something like a boolean, and so that you just get unlimited access to the data.